Hello guys, this is Edward. Welcome to another mass spectroscopy lecture. And previously I have explained how to analyze mass spectrum and deduce the molecular structure of analytes. So today I'm going to be discussing how to sketch possible mass spectrum of analytes. Okay, and if you haven't done so, kindly subscribe to my channel, like the videos, drop a comment if you have any question, and do not forget to turn on your notification bell so you get to be notified whenever a new video like this is dropped. Okay, now we have a question here that says sketch the expected spectrum for 3-methyl heptane. Include details of the reasoning in deducing the spectrum. So the first thing you're going to do here is to write down the structural formula or molecular structure, a molecular structure of 3-methyl heptane. Okay, so we draw the structural formula for 3-heptylmethane. We have CH3, CH2, 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 1, 2, 3, 4, 5, 6, and CH3. This is heptane. Then we have methyl on carbon atom number 3. Okay, CH3. Okay, now this is the molecular structure of 3-methyl heptane. Now the idea is this: we are going to look at the possible fragmentation of this analyte, okay, and take note of the fragment and the value of each of the fragments. Then from there, we can then sketch our spectrum. Okay. Now, after writing down the structure of the analytes, then the next thing to do is to look for the molecular ion of the analyte. Okay. Our M plus will be that for 3-methylheptane is 114. That is the molecular ion of the analyte. Now, then let's look at the possible fragmentation. To do that, I will number the carbon atom. 1, 2, 3, 4, 5, 6, 7. Okay, so now we'll look at the possible fragment when carbon atom number 1, the bond between carbon atom number 1 and 2 is broken. So when we break the bond between carbon atom number 1 and 2, what are the possible fragments? We're going to have this fragment on the left hand side, which is a methyl carbocation, okay, and the fragment on the right hand side, which is basically a 2-methyl hexane, okay, 2-methyl hexyl carbocation, right? So that is the cation on the right hand side. Now, what is the value of methyl carbocation? That is 15, okay, and the other value of the cation on the right hand side will be 114 minus 15, right? Okay, so but before we do that, now after writing down our molecular ion, then we look at if we have any isotopes. Do you have any isotopes here? Isotopes. There is no isotopes in our structure, so no isotopes. Do we have nitrogen present? There is no nitrogen present, right? Now, then we'll start writing down our peaks, okay? Our peaks that is from our fragment. So if you break bond between carbon 1 and 2, we're going to have fragments of 15, and that is for the methyl fragment, and then methyl hexyl fragment on the right hand side will be 114 minus 15, and that is 99. So we are going to have fragments of 15, and you're going to have peaks on 15 and 99. Okay, now what if you break bond between carbon number 2 and carbon number 3? So if this bond is broken, so we're going to have on the left hand side, we're going to have an ethyl carbocation, right? We're going to have an ethyl carbocation on the left hand side, and then the value of ethyl carbocation here is 29. Okay, so if you have 29 on the left hand side, then on the right hand side we are going to have 114 minus 29, that will be 85. So you're going to have peak at 29 and peak at 85. Okay, now what if you break bond between carbon 3 and carbon 4? Okay, now here we're going to have this carbon 3 here. If you break this bond, you're going to have this fragment on this side, right? You're going to have this fragment, and if you take note, this carbon here is a secondary the secondary propyl carbocation, and that is where we have the most stable fragment. Okay, because we have that most stable fragment, so any fragment from this side will become the base peak. Okay, and if you find the value of this fragment here, it's going to give us 57. So if you break bond between C3 and C4, we are going to have 57. That is from this side, and then also on this side as well, we're going to have 57 from this side as well. Now, what if you break bond between C5 and C6? If you break bond between C4 rather, C4 and C5. If you break bond between C4 and C5. Now, on the right hand side, note you are going to have a propyl carbocation. This propyl carbocation. Okay, and the value of propyl carbocation is 43. Okay, and on the left hand side we're going to have this other carbocation here. That is a 2-methyl butyl carbocation. Okay, and remember this also here we're going to have a base peak at carbon number 4, because it's also a stable carbocation as well. Okay, so it's also a stable carbocation. We're going to have a base peak, a prominent peak at carbon number 4 as well. All right, so if you break bond between carbon 4 and 5, you're expecting to have a peak as a result of propyl, and that is C3H7 carbocation, and that value is 43. And we're also going to have peak at 71. Okay, now so we have these are the possible fragments, because if you break bond between 5 and 6, we are going to have ethyl. So basically this, you've gotten this already, so there is no need of repeating it again. Right, so these are the possible peaks that we are going to get. Now, which of them they have to identify? Which of them is the base peak, like I've explained, the prominence peaks, and the significant peaks. Some peaks are significant, okay, some are not significant. Okay, so here our base peak here is 43, 57. Okay, due to the stable carbocation, all right, on carbon number 3 here. All right, and also you're going to have another very prominent peak at 43. Now this peak is usually the characteristic peak for alkanes due to the fragmentation of propyl carbocation. Okay, now 85 is a prominent peak, is a significant peak. Okay, 29 also is also a significant peak because of ethyl carbocation. All right, then 71 are not that prominent, they're not that significant. They will appear though, but they are not that significant. 99 as well. 99 and 15 are not that significant, because mostly methyl carbocation are usually not stable, right? So they easily, they are not stable basically, so the fragments will not be that abundant, will not be prominent. So we're going to have a non-prominent peak at 15 as well, 99 as well. So these two fragments, 2 peaks at 15 and 99 will not be prominent. Okay, so now having known this, let us draw the possible structure, let us sketch the possible spectrum, of this analyte. So we're going to have our relative abundance on this axis. So let me use another color. Okay, we're going to have relative abundance on this axis, and then our mass to Z ratio, mass to charge ratio, that's our M to Z ratio, will be on this axis, M to Z. Then we have our relative abundance. Now remember, your sketch doesn't have to be 100% accurate like I explained. Okay, just put the necessary details on your sketch. Okay, so the first thing to include there is our M plus molecular ion, which is 114, and molecular ion is not usually that prominent. Okay, we have our 114. Okay, so the next peak in terms of bigger number, okay, is after 114. In terms of bigger number is 99, right? And 99, like I said, is not a significant peak, so it's going to be small. So we're going to have our 99 somewhere here. 99. And after 99, in terms of big number, we have 85. Now 85 is a significant peak. Okay, is a significant peak. 85 is a significant peak. So we're going to have a significant peak at 85 here. And after 85, next of bigger number is 71. 71, like we said, is not it's not prominent, so we're going to have 71 here. After 71, in terms of bigger number, is 57, which is the base peak. So we have 57 here. Okay. Now after 57, the next number is 43, and 43 also is a very prominent peak, and it's the characteristic peak for alkanes. So you're going to have 43 here. Peak at 43. After 43, the next number is 29. So expecting 29, peak at 29 here. You're going to have peak here, and like I said, it's prominent. It's significant. Okay, it's a significant peak. It's a significant peak. So you have 29 here. After 29, the last peak is 15. 15 methyl cation is not usually prominent. Sometimes it might not be visible in the spectrum. Okay, so let's just put this as our 15. Okay, now this is a sketch of our spectrum. Remember, you could have other peaks that is as a result of loss of hydrogen. For example, if you have loss of hydrogen from this butyl carbocation, here we could have another peak at 56. Okay, and you could also have loss of hydrogen from propyl carbocation, and you have another peak at 42. So you can have also peak at 84 as a result of loss of hydrogen. Okay, and so on. So you just put other peaks as a result of loss of hydrogen, and that is it. You can also have 28. So this is a sketch of spectrum of 3-methylheptane. I hope that makes sense. So let's look at another question, another example. So